thank you. So a little bit about myself, David Karamgard. I'm a committer on the Apache Pulsar project. So this is a little bit biased and based on our research from what we learned on the Apache Pulsar project about metadata. Obviously, I've worked at a lot of different places there, from A to Z, Amazon to Zappos. Formerly worked in big data space as well, like our previous speaker. So a lot of experience with Kafka, NiFi, things like that. I want to talk a little bit about our Zookeeper replacement story, right? So Kafka had a big one with KRAF, and I'll get to that a little bit about how Zookeeper has kind of become a bit of a pain for everyone who uses it. It kind of got a bad name. It's a great system for what it was designed for, which was distributed coordination. But it's one of those few systems that are designed to be horizontal, but can't scale horizontally, right? It suffers from this system where as you add more machines, the performance gets actually worse because you have to get a consensus among more machines. So it's easier to get a consensus with 3 or 5 machines. If you go to 33 or 55, then you have too much networking traffic, and it just doesn't work. So you really can't scale the system. It was designed for things like service discovery, leader election, distributed lock sort of coordination. That's what it was built to do. That's what it was designed to do. It was not designed to be a distributed database. It was not designed to store metadata. But when you have distributed system messaging systems like Kafka or Pulsar, you have to store this metadata somewhere. And since it was already there for your distributed coordination and locks and handing off who owns what topics and so on and so forth, obviously as developers we said, well, let's just put some data in here. It's not gonna really matter much, but eventually became one of those decisions that ended up impacting us, and we had to retrofit and get rid of it because it becomes a system that just doesn't work under system. So you keep things like listed nodes in the cluster, location of the data, cursor offsets, topic policies, metadata, things like that. So that's what you're trying to store in your metadata storage. And there still are no good solutions. I'll make that statement now, including KRAF to that, because there was things like Zookeeper itself had major flaws, like I mentioned, horizontal scalability limitations. You can't add more nodes and make it perform better. It just doesn't work with that system. And you can't really scale vertically. You can do some patching and stopgap things, increasing the resources and I/O to it, but it doesn't resolve the fundamental underlying problem, which is it stores data inefficiently. The way that you store metadata in Zookeeper or etcd, these other similar systems, is you have a snapshot of the data, you take 1 or 2 gigabytes of data, update it all at once, and then flush it back to disk, right? And so you do these periodic snapshots, and that puts an upper bound on how much data you can manage and store efficiently, right? The bigger these snapshots get, the longer your pause is to publish that data to disk, and it becomes an I/O resource bottleneck, and it really doesn't scale, so it's sort of a problem that everybody had. And this inelastic metadata store had some practical impacts, right? It wasn't just a performance thing, it wasn't just a theoretical concept. It really put a lot of limitations on cluster performances and how big your clusters could be and how they could perform. Like, so I'm unaware of any Kafka cluster with more than 1 million topics. Maybe I'm wrong, but they generally started to struggle at 500,000, maybe with KRAF to get a little bit bigger. From the Pulsar world, we had similar limitations. We get to about 1.5 million topics. We'd have to tune the heck out of Zookeeper to get it to work, to get it to store the metadata that we needed. And as that got bigger and bigger, your cluster performance suffered, right? It was just a degradation thing. Again, you're taking these big snapshots, flushing them to disk. Everything's pausing and waiting, so it became a real part of the problem, and you try and scale these things up, and you do efficient tuning and sizing, monitoring became an expert's job, and it's very, very hard to do. It takes a lot of work. So obviously I'm not gonna hurt anybody's feelings here. KRAF came along, that was Kafka's solution to it, like, hey, we'll get rid of Zookeeper complexity for you. Who wants another system to manage, right? It's something else you have to manage, it falls over, it fails a lot. If we just get rid of it, things will be better. But we fundamentally disagree with the approach that they took, that they basically decided to re-implement Zookeeper itself, but stuff it inside your brokers, right? So if you read the literature itself, they've taken and re-implemented the Paxos consensus algorithm, and they basically didn't improve any scalability issues, right? So when you spin it up, and your first 3 brokers that come along, they become your de facto Zookeeper nodes of what they used to be, right? They become special nodes that can't fail, they become your consistency, and they run this data inside the broker. And it really doesn't, again, it suffers from the horizontal scalability issue, right? You're going to still have these issues just because of the way it's architected. So why are we interested in that? A little bit about Pulsar for those of you not familiar, because I'm sure not a lot of people are familiar with that. Everybody knows Kafka. We do basically what Kafka does, but we separate the storage and compute, which is why metadata is a bigger thing to us. So our brokers are stateless, they can serve any topic. We store data in a separate scalable storage layer called Apache Bookkeeper, and then our metadata storage is critical for us because it keeps the pointers of, hey, where's that data for topic A, B, and C? We go to our metadata storage to figure out where in Bookkeeper or where in S3 we've offloaded those segments, where to read that data from, in addition to all the other things we listed in the earlier slide about who's in the cluster and what are the policies and things like that. So it becomes a critical component for our architecture. So as you can see here, we used to use Zookeeper. That was sort of the de facto thing. We suffered through all that pain, same as everybody who had to deal with the scalability issues with Zookeeper. And we looked at what the Kafka community was doing, and we said, well, they're just really re-implementing it again. We want to have a different solution to that. So we replaced it with this little pinwheel icon here, which represents Oxia, which is a new open source project. It's under the Apache license, and we've released it to the open source. And we'll talk a little bit about it, and we've already used it, and we're seeing some good results. So we'll talk a little bit about Oxia. So it is designed to be a fundamentally different way of storing the data. That was a fundamental bottleneck with Zookeeper. So we came with a more scalable, truly horizontal scalable metadata store, and took a different approach than what Zookeeper did in the past. We said, we're not going to redo this again. We're not trying to implement a distributed consensus algorithm again. Been there, done that. And the goal was to support clusters that have hundreds of millions of topics without a lot of specialized hardware. We just want it to work natively. You don't have to specialize tune it. If you want to just have one big cluster to support as many tenants as you want, as many topics as you want, this Oxia would be the solution. And again, as I mentioned before, it's released under ASF 2.0 licensing. So again, it addresses some of the performance issues that are currently used in the space. Again, Zookeeper and KRAF, we think they still suffer from the same fundamental flaws of horizontal scalability, which again impact your cluster's ability to serve multiple topics and things like that. So we designed it for a cloud-native Kubernetes environment, transparently horizontal scalable. As you add more nodes to your Oxia cluster, you'll be able to store more data. You're not limited to any of the snapshotting that you see with etcd or Zookeeper or KRAF. We wanted linearizable per key operations, so as you scale up, it's going to be a consistent cost, and able to sustain billions of reads and writes per second, store lots of data, all these things that you need to do to have a truly scalable metadata store. It becomes almost like a distributed system unto itself. So this is our fundamental architecture of Oxia. For those of you might recognize this. We follow a little bit from where Kafka stores data, but it's a good way to do this thing where you have a client that comes in, and there's a scalable in the green is your storage layer. These are your storage pods that store the metadata. So we don't have a single consensus. We have multiple copies, so you have replication built in, so you have redundancy built in. And then there's a separate Oxia coordinator system there, which you can configure with a cluster status using a config map. So you just say, I want my storage pods to look like this. I want them deployed here. I want this much RAM and CPU and all these sort of things, and then Kubernetes does its magic like it always does. You declare what I want the state to be, so let it be written in the cluster, Kubernetes make sure that that's exactly what it looks like. And then you have and that's all controlled by an open source K8s, a Kubernetes operator that does all those sorts of things. So you just say, I want my cluster to look like this, and that's it. So the coordinator part is responsible for performing all the error detection and recovery. So it is publishing out to this data, it's replicated multiple copies, and it makes sure that all of your data is in sync. If there's any sort of issues or any storage pods fail, it's going to spin up another one for you automatically. So again, you can scale horizontally, store as much data as you want. It coordinates amongst the storage nodes itself and decides which one is going to be the responsible one for storing that metadata. So this is where we use a leader-follower consensus algorithm, different from a Paxos. We have, similar to those with Kafka, and you have replicas, you have a leader replica, and everybody else sort of comes around and synchronizes with that. We use that same distributed algorithm for our storage nodes because it works. It works well for storing large data volumes. It's not great for metadata and things like that or it's good for metadata and things like that. And it also does the checkpointing. So periodically it'll do these checkpoints that you had to do in Zookeeper, which are very expensive, and instead it handles all that for you. So it tracks the leaders and knows which storage pods are responsible at what point in time. So the coordinator knows, hey, I want to go back and find this piece of metadata. It can point you to the right storage node that has it, which one's the leader for that. The storage pods are really the horizontal scalable part. Throw as much disk at it as you want, designed again with the leader-follower replica. You elect this particular storage pod to be in charge of this particular piece of metadata or metadata associated with it, and it's in charge. So you can scale out horizontally your storage as much as possible. Again, it's controlled by the Oxia coordinator, and it's used to form, you can form ensembles so you can get these consensus, right? You want to have 3 replicas. The data, you can have, copy on storage pod 1 and 3 and 4. 1's the leader. 3 and 4 are there for standby in case something fails over. But it doesn't provide these additional checks against other ones, right? It's up to the coordinator to determine whether the storage pod is up or down, so they don't have to have cross traffic, right? And that was the horizontal scalability Achilles heel of Zookeeper, right? They have to talk to one another all the time. What do you think the value of this particular metadata is? I think it's 1, I think it's 1, I think it's 2. Well, I guess it's 1 because 2 out of 3 wins, and that's just how you do consensus. We got rid of that side chatter, so it makes it horizontally scalable as well. Data replication, as I mentioned before, is, for those of you coming from Kafka, leader-follower. One guy's the leader, everybody else comes along and gets themselves up to date eventually to achieve your redundancy that you want. The leader, again, it's using a write-ahead log, a very simple data structure. Publish the data in, store the metadata there, and then you have these key value stores for optimized lookups as well. Once it receives an acknowledgement back, it forms the ensemble and says, okay, everything is good, and applies the changes there. So it's a consensus done on write sort of mechanism, but this is how it works. So it's very scalable. If you want to add more nodes, you just add new leaders, new followers, things like that. It just scales that way. So I alluded to it a little bit earlier, but it is truly scalable. It basically shards the data set, right? When you had, in Zookeeper, as I mentioned, or etcd, these consensus stores, you would have these large snapshots, and the more metadata you tried to stuff into the system, the longer it took to take that data out, update it, and then put it back to disk with these snapshots. So we've taken that data set, that metadata set that was a limitation, and cut it up into individual shards and assigned it to different storage nodes, and now you can scale horizontally. There is no single bottleneck. There is no one I/O operation that bottlenecks you. Now it's done across multiple storage nodes in parallel. The shards are assigned to all the available servers. When the cluster expands or shrinks, the shards can be reassigned as well, so they don't live on that node. You can add more storage nodes. You can also scale down. If you decide, hey, I don't need this much metadata anymore, I'm scaling down. And then they auto split. So you make this decision once that this shard is going to be assigned to the storage node, you're not stuck with it. If that storage shard becomes too big to overwhelm the storage node, we can easily split it because there's no reason not to, right? You can easily do this. They're not assigned to anything. Shards are static and be created dynamically, reassigned, split in half into 2 new shards, et cetera. So it really doesn't ever become a bottleneck from a storage perspective either. And like I mentioned before, you see this historically, Zookeeper had these storage limitations around 2 gigabytes because you're trying to take these snapshots. Oxia is designed to store the metadata differently, larger than RAM you have available in orders of hundreds of gigabytes across multiple shards. So you can do it all in parallel, again, do it horizontal, and eliminates the need for periodical snapshots, kind of a summary we talked about in the previous points, right? So you don't have this cross coordination, you don't have these bottlenecks that you have in these other systems. This makes it much more scalable because we've architected out the horizontal scalable problem you have with Zookeeper, and we architected out the size limitation strength to have these capabilities, right? So you can try Oxia, it's open source. You can scan that query code there. You can also go directly to the GitHub repo. It's available, download it. We've preliminary tested, I guess I should add a slide for this. We've done it in production. We were typically limited to about 1 million topics per pulsar. With the first iteration of Oxia, we were able to do 10 million, no problem. And also saw some different performance improvements overall, 30-40% throughput performances as well, because those periodic pauses that you get with the metadata store didn't impact performance. So it's really preliminary results have proven well, and we're well on our way to our goal to having hundreds of millions of topics. So with that, I have about 5 minutes left. Are there any questions from the audience? All right, thank you very much.